This video will discuss Grimme's vibrational entropy correction, which affects the main property we want from the calculation, which is free energy. As we know, the free energy G is equal to the enthalpy H minus the temperature T times the entropy S. And this is precisely what the frequency calculation allows us to obtain. In the case of entropy, we can decompose it into multiple terms. So the translation, rotation, vibration, and the electronic entropy. Most of these terms are relatively straightforward. So for the translation, it's 3/2 of RT. In the case of electronic entropy, we can consider at reasonable temperatures that the electronic transitions essentially don't occur, which means that the entropy only comes from the ground state multiplicity. The rotation entropy is also relatively straightforward and is given by different formulas depending if we have a single atom, a linear molecule, or a more complex molecule. The most complicated term is really the vibration, which is obtained from the frequency calculation, so the frequency modes, and is given by this formula. And actually, if we plot this formula in function of the vibrational frequency, we can see that for very low frequencies, actually we have an asymptote that goes to infinity, and that of course doesn't seem quite reasonable. This method of calculation assumes a harmonic oscillator, and if we have a very low frequency, things start to break down, and we have this odd behavior. And this means that if you have very low frequencies in your calculations, the entropy won't get calculated right, and your free energy won't get calculated right. But you might think that you would never have so low frequencies, but actually now that computers are getting quite powerful, we can treat quite big systems, and for example non-covalent adducts, which typically have those low frequencies because multiple parts of the system aren't covalently bonded, so it's quite easy to move it around. The first solution was proposed by Truller and Grimme, which is quite straightforward. Since the low frequencies cause problem, let's just assume they're not so low. Let's just assume that everything below a certain threshold, say 100 inverse centimeters, is just calculated as 100 inverse centimeters. So you just apply this cutoff and you kind of get rid of the problem. But of course this is not necessarily the best way to handle this problem, as it's a bit simplistic and doesn't seem quite physically sound, which is why Grimme proposed a more elegant solution. And actually his proposition is that the low vibrational modes should be treated as rotations instead. So here I've plotted the rotational entropy, which is a bit more well behaved and is more suitable for those low frequencies. So now the only issue is, where do you transition and how do you transition? Of course you could imagine simply switching at a certain threshold, but then your function won't be continuous, which is not particularly nice. So to make things quite smooth, Grimme proposed a smooth switching between the two, which looks like this actually. So around a certain threshold, you have a nice transition between the two with some parameter alpha, which can be tuned to change a bit the abruptness of the change, but really the differences are minimal. So with the default parameters, it looks like this. It's a bit more elegant than the previous solution. So in his work, Grimme developed this method and then used it for these kind of adducts, which are non-covalent adducts and are quite large, which means there will definitely be very low frequencies. He calculated the formation free energy for a series of this kind of adducts and compared it to the experimental values. In computing the free energies, he used his new correction to make sure to avoid the errors from the low frequencies he obtained. And here I've plotted the results, and we see a quite good correlation considering the size and complexity of these systems, and of course the limitations by the computing power. Since these adducts can be very large, the calculation time must be quite significant. Here are the references for the two different corrections if you want to have a bit more details or see exactly what structures were used. As for this video, we'll go a bit more into details of how you actually apply this correction in practice. So here I have pre-computed a typical non-covalent adduct, so a benzene dimer. If we open it up, so if we look at this frequency mode, this is clearly a vibration, but if we look at the lower frequency modes, this looks a lot more like a rotational, at least not clearly a vibration, since you can't see any of the bonds really vibrating. This is really the two benzenes kind of twisting. This kind of justifies Grimme's approach. So how do we actually apply this correction? Well, we could code some script that would read all the frequency modes and compute the relevant corrections to the enthalpy to get us to the free energy. But of course, if we don't want to do that, other people have done it already. So in particular, I'll talk about good vibes, which I will link in the description. So to call this package, you simply do your Python version -m good vibes, and then specify the log file, and it will compute here all the relevant properties. You have the electronic energy, 0-point energy, enthalpy, then TS, and here this TS QH is a quasi-harmonic, so this is the correction, considering by default Grimme's correction, and this is our final free energy with Grimme's correction. If we want, we can change the frequency, the cutoff frequency. By default it's 100, we could specify 50, and we see we get a slightly different energy. Similarly, if we want the correction by Truller, we can specify QS Truller, and it will compute it according to Truller and Kramer's correction. So you can see have a slightly different free energy again.